The quantum measurement mystery. Picture a coin spinning in midair. It's not heads, not tails, not yet. It hovers in a cloud of possibility. Now imagine this coin isn't just metaphorical, but real. Not made of metal, but of quantum probability. And only when you observe it, truly observe it, does it pick a side. Heads, tails. One path chosen from many. This isn't science fiction. It's quantum physics. And at the heart of it lies one of the most unsettling questions in science. Why does observation change reality? This is the measurement problem, a mystery that refuses to yield even after a century of asking. In the quantum world, particles like electrons don't behave like solid, defined objects. They exist in superpositions, multiple states at once. An electron can be here and there. A photon can go through one slit, or both. Physicists use the wave function to describe this haze of probabilities, a mathematical form of maybe. But this wave function isn't just a tool for prediction. It seems to be reality itself, before anything happens. But then we measure, we observe, and suddenly the wave function collapses. The haze clears. The electron picks a spot. The photon chooses a path. This collapse is at the center of the mystery. What causes it? Why should a particle behave differently because it's being watched? The famous double-slit experiment illustrates this beautifully. Fire single particles at a screen with two slits, and you get an interference pattern, evidence the particle behaves like a wave. But if you place a detector to see which slit the particle passes through, the interference disappears. The particle behaves like a particle again. It's as if the act of measurement rewrites the outcome. Some interpretations say measurement forces reality to choose, but they rarely explain how or why. The Copenhagen interpretation accepts collapse as fundamental. The many worlds interpretation claims no collapse happens at all. Every possibility unfolds in a parallel world. Others propose decoherence, where the environment measures the system for us, or that consciousness itself triggers the collapse, suggesting that awareness shapes existence. But the question lingers. Does reality exist when unobserved? Or do we bring it into being by looking? And if observing can shape outcomes, what happens when we observe continuously without pause? In our next mystery, we'll explore a paradox where merely watching may freeze time itself. The quantum Zeno paradox. They say a watched pot never boils. But what if, on a quantum level, that's quite literally true? What if time, that relentless river, could be slowed or even stopped just by paying close enough attention? This isn't just poetic musing. It's a real paradox, known as the quantum Zeno effect, a mystery that shows us how watching reality too closely can paralyze it. In quantum mechanics, particles can change states over time, like a radioactive atom that eventually decays. But there's a catch. If you check on the atom frequently enough, its decay can be delayed, even prevented. This is the quantum Zeno effect. Named after the ancient philosopher Zeno, who proposed paradoxes about motion like Achilles never catching the tortoise, this modern twist is backed by experimental evidence. How does it work? Quantum systems evolve probabilistically, but each measurement interrupts that evolution, essentially resetting the system. So if you observe a quantum state over and over in rapid succession, you collapse it back into the same state repeatedly, and it doesn't get the chance to change. This leads to a strange conclusion. Observation can control reality, not just passively record it. Watching a quantum system is like constantly shaking a snow globe, never letting the flakes settle. The act of measuring disrupts the natural flow of time and change. But here's the kicker. The effect fades if you stop watching. The moment your gaze slips, the system snaps back into evolution. It changes, decays, moves forward again. It suggests that the passage of time itself might be more fragile than we thought. That maybe time is not a river, but a construct built from change. And change from observation. Could attention be a force, not psychological, but physical? if observation can stall time? What happens in places where time breaks down completely? Let's venture deeper, to the edge of space and the end of meaning itself, into the heart of a black hole. The black hole information paradox. Imagine a vault so secure that nothing can escape. Not light, not matter, not even the memory of what entered. That's a black hole. But what if this vault does something worse? Not just hide information, but erase it from the universe entirely. This is the heart of the black hole information paradox, a puzzle that pits two of our best theories, quantum mechanics and general relativity, against each other in a cosmic duel. According to Einstein's relativity, black holes form when matter collapses under its own gravity, warping spacetime into a point of no return. Anything that crosses the event horizon, the boundary, is gone. Forever. But quantum mechanics has a rule. Information, the record of what something was, can never be destroyed. It can be scrambled, hidden, transformed, but not erased. That's sacred. Stephen Hawking added a twist. Black holes aren't entirely black. They emit faint radiation, now called Hawking radiation, and over time, they evaporate. But Hawking's calculations suggested that this radiation carries no information about what the black hole swallowed. So when the black hole vanishes, so does the information. Gone, violating quantum law. This contradiction has shaken physics for decades. If information can disappear, the universe becomes unpredictable. The past could be erased. Time could become a dead end. Some theorists believe the information is subtly encoded in the radiation. Others say it's preserved on the event horizon, like a hologram on a cosmic billboard. There are even proposals involving wormholes and quantum entanglement across spacetime. If black holes can store or destroy memory, then perhaps the universe is more like a conscious dream than a deterministic machine. And if information can vanish inside darkness, what about the vast lightless stretches between stars? Let's explore the empty spaces of the cosmos, where nothing turns out to be not so empty after all. The vacuum energy puzzle. Look around you. Even in a dark, silent room, between the atoms of your skin and the void between stars, there is no such thing as true emptiness. The vacuum, far from being nothing, is one of the most energetic places in the universe. But here's the paradox. It shouldn't be. Or at least, not like this. Quantum field theory tells us that what we think of as empty space is actually a seething froth of particles and energy, constantly appearing and vanishing. These fluctuations give rise to a form of energy known as vacuum energy or zero-point energy. Now, here's the staggering part. When physicists calculated how much energy this vacuum should contain, the result was absurd. That's a number with 120 zeros, the biggest mismatch between theory and reality in the history of science. Why is there such a huge discrepancy? Is something canceling the vacuum energy almost perfectly? Is our understanding of gravity or quantum mechanics fundamentally flawed? Or is there a hidden symmetry we haven't yet discovered? This puzzle also connects with the cosmological constant, the term Einstein added and later retracted from his equations to explain why the universe doesn't collapse. It now helps explain why the universe is expanding faster and faster, driven by what we call dark energy, possibly linked to vacuum energy itself. Are we missing a deeper law of nature? Is the vacuum a key to unifying quantum physics and gravity? But beyond every equation, every particle and wave, one question lingers. One mystery that wraps all the others in silence. Why does the universe exist at all? Why is there something rather than nothing? Close your eyes and imagine the total absence of everything. No stars, no atoms, no space, no time, not even the possibility of those things. This is nothing, and yet, somehow, we live in a universe that is clearly something. Why? This question isn't just philosophical. It may be the ultimate unsolved mystery in all of physics. Physicists can describe how the universe evolved from the Big Bang, but not why there was a bang at all. Some theories suggest that particles can spontaneously appear from a quantum vacuum, but a vacuum is still something. Others imagine a multiverse where our universe is one bubble among many, but again, that only moves the question back a level. Could nothing be unstable? Could reality arise not from cause, but from the impossibility of true nothingness? If existence is the default, not the exception, then perhaps all our assumptions are backward. Maybe reality doesn't need a reason, or maybe meaning itself is what creates reality. This question ties together every mystery we've explored: the measurement problem, the collapse of wave functions, the erasure or preservation of information, the invisible energies of the void. All hint at something deeper, something we may not yet have the language to express. Why are you here? Why am I? Maybe the universe is not a puzzle to solve, but a story being told, one we are part of, even in our sleep. And so, as you drift off, wrapped in starlight and paradox, remember, not knowing is its own kind of peace. Let the mystery cradle you. Let the silence speak. The universe is wide, and so is wonder.